Hi everyone, thanks for checking out this video. So this is going to be the next video in the series I'm making on basic transcriptomic analysis. So if you guys remember in the last video, I showed you guys how to read this data set we downloaded into R and how to do some like basic processing and then save these R objects with the data matrix and the classes for each sample we're dealing with. And in this video, I'm going to be showing you guys how to do the actual differential expression analysis. And we're going to be using this package here called DESeq2. I think this is probably the most popular R package for doing differential expression analysis. It's at least the one I've seen used the most. So yeah, that's going to be the topic of today's video. Okay, so let's get started. So like usual, I always have this line at the top to just clear the environment if I need to. And then, like I showed you guys in the last video too, whenever I'm dealing with real data, I like to put as a comment the link to where I got the data. So if you guys haven't downloaded already, you guys can download this the data set at this link here. Remember, this is the Geo website where you can find all these publicly available data sets. Okay, and then the other thing I like to do is when I'm using a package that that is something external that I had to install. If I think other people might be looking at my code, I'll leave a little comment telling everyone how to install the package. So if you guys don't already have DESeq2 installed, you're going to first run this command here, install.packages biomanager. I'm going to just run that in the prompt down there. And that's going to install this thing called biomanager, which is basically like a package manager for this thing called bioconductor, which is like bioconductor basically has a lot of different bioinformatics related packages and lets you install them in R pretty easily. So you're gonna run that command first, and then next you're gonna say biomanager : install DESeq2. So just run that right down in the command prompt there. But okay, so once you guys have that installed, you should be able to just run this command here and load it in. Okay. And yeah, so now to get started, if you guys remember from the last video, we ended the video by saving these R objects we had to RDS objects. So now we can easily read them back in without having to do all the like data processing again. So I'm going to say here data arrow equals read RDS. Remember, that's how we read in this saved RDS object. Then just the path to it. So RDS objects / filtered data dot RDS. Okay, run that. Hopefully it works. And then same thing for the filtered classes. And now with the new variable names, I'm not calling them filtered anymore. I'm just calling them data and classes. But if you guys remember from the last video, we did do some filtering. So we filtered out that CHP disease, all the samples from that. So now if you check the classes here, all we have is the control samples and the IPF samples. And if you guys forgot, IPF is this disease we're interested in studying. It's a lung disease called idiopathic pulmonary fibrosis. Basically just a disease that involves scarring of lung tissue that the cause of it is unknown. So we have 103 of those disease lung tissue samples, and then we have 103 control healthy lung tissue samples. And then if you guys remember data, like this data matrix we have here, although it's not literally a matrix, it's actually a data frame, but you know, you guys know what I mean, matrix. Not literally the R object called a matrix, but basically a data frame in like matrix shape kind of. So we have 18,838 rows, where remember each row represents one of the genes. and 206 columns. Where remember these are the samples. And then our class's vector basically just tells us for each one of these columns what class it was. Was it a control or was it a IPF sample? So yeah, we have a label for each column in this thing. And if you guys wanted to, just remember you guys can get the names of all the genes just with row names data. That's all the names of all the genes because they're the row names. And then column names data will give you the sample names. Okay, so now we've got that read in. Now we're ready to start using this DESeq2 package to actually do the differential expression analysis. So the first thing we need to do is we need to just prepare some of this information to actually put into DESeq2 so they can do the analysis for us. So what we're going to do here is we're gonna make a new data frame called samples underscore info. You guys can call it whatever you want, but I think that's what makes sense to call it. And then data frame parentheses, and then we're going to say condition equals factor classes levels and then control IPF. Okay, so this looks a bit complicated, but basically this is just making a data frame that we're gonna pass into DESeq2 to tell it this information that we have about the label of each sample and which class it belongs to. Because we have this like string vector here. Classes here is like if I remember correctly, I think it's just like a string character vector. Whoops. Yeah, it's like a character vector. But we need it in a format that DESeq2 can recognize, so that's why we're here just factorizing it, I guess. And then defining the levels as control and IPF. And the order here, by the way, is what's going to tell DESeq2 which one is the base condition and which one is the comparison condition. So the first one is the base condition. So we made that the control, and the second one is the comparison condition. So when we're eventually hearing about like upregulated genes, those are genes that are going to be upregulated in the comparison condition with respect to the base condition, and downregulated vice versa. But yeah, basically here we're just putting this information into a data frame that we're eventually going to pass into DESeq2. So yeah, just run that. Okay, and we need to make sure that the row names for this data frame that we just made, we just want that to be the same as the column names for the data. So basically, remember the column names of the data is all of the sample labels, not the class they belong to, but literally like the actual class and then these like ID numbers. So these are unique to each sample. So we want to make these column names from data, and we want to use these as the row names for this new samples info data frame that we're making. Okay, again, yeah, just getting ready to pass this into DESeq2. Yeah, like basically, if you guys haven't realized already, basically DESeq2 is going to pretty much do everything for us, and all we need to do is make sure we're packaging this information correctly to pass into DESeq2, and then from there it'll take care of like all the actual analysis. So for the next part, I'm actually going to be a little bit lazy and copy and paste this part, because I don't feel like typing it all out. But yeah, so this part here is we're going to be actually making, we're taking this information, including this this data matrix here with all the counts that we have, and then the samples information with the conditions. We're taking all this information and we're using it to create a DDS object, where DDS stands for DESeq data set. That's the type of object we're making. It's basically like a counts matrix, except it's got all of this information like properly stored in it. So yeah, let's run that. But yeah, so now we have this DDS object. If we want, we can look at the class of it. Yeah, it's a DESeq2 object. We can also look at the dimensions of it. It has the same dimensions as our original data matrix here. It's got a row for every gene and a column for every sample, but we've included in it this information about which condition all the samples belong to. So basically, we're getting it ready to do this differential expression analysis that we're going to have DESeq2 do for us. By the way, so something important that maybe I should have mentioned earlier, but I'll just mention it now. So to use this package, to use this package DESeq2, you're really supposed to have the count data. You're really not supposed to have like data that's already been normalized. You don't want to have like TPM data or like normalized gene expression data like that. You want to have the raw counts matrix because DESeq2, when it's doing this analysis, it does it uses its own like internal statistical methods to do its like own type of normalization and to compute its own statistics with its own methods. And basically, all of these statistical methods that it's using internally assume that you're dealing with count data, not with normalized expression data. So that's why when we downloaded this data from Geo, I made sure to get the counts matrix. And like an easy way to know if you have a counts data set is that typically it'll look like the measurements are integers. If we were seeing like floating point decimals here, that would be a sign that the data set probably has already undergone some kind of normalization. But since we're seeing integer measurements here in this matrix, that suggests that we're dealing with a counts matrix. So yeah, that's what we need for DESeq2. Kind of annoying. It doesn't really. It's not supposed to work with like already normalized data. So unfortunately, if your data set you're trying to work with is already normalized and you don't have the raw counts data set for it, then you might be out of luck here. But yeah, I mean, it is what it is. So okay, so moving on. So now we've made the object that we're gonna use to actually do this differential expression analysis. So next we're gonna actually do the analysis. So I'm gonna say DDS arrow equals DESeq and then DDS. So we're basically going to do this analysis on this DDS object here and reassign it as its new value, basically. Okay, so this might take a minute or so, but yeah, we'll wait for it. So yeah, some of what it's doing here is, like I was saying, how it has its own internal methods for doing its own normalization. So this like estimating size factors thing and like estimating dispersions, this is its own internal normalization it's doing to correct for sequencing depth between the samples. And yeah, gene-wise dispersion estimates, again, some like internal statistics. Yeah, so it does these things kind of all internally. And by the way, this is one advantage of using DESeq2 rather than trying to like hard code this kind of analysis yourself, is that you don't have to figure out how to do all these statistics yourself. It kind of just does a lot of this for you. So it makes it nice and easy. It has these methods that are reliable. So yeah, you don't have to worry about like figuring out how to come up with your own statistical test or something. It'll just kind of make that easy for you. Okay, so now the analysis is complete. So now we're going to pull the results out of here. So we're going to say results arrow equals results DDS. Okay, so run that. And okay, so now we have now we have these results we can look at. So let's just take a look here. So we can say head, because this is going to be a long thing. Let's just look at the top of it. So yeah, basically it gives us this table where each row is one of the genes, and then we have some information about it. So we have the base mean here. So this is basically like yeah, like the base expression. Log2 fold change. So this is basically the yeah, just the log2 fold change of the expression in the IPF samples compared to the expression in the control samples. This thing here, LFCSE, is the log fold change standard error. Basically, just a measure of the confidence of this log fold change. So a smaller number here means that we're more confident in this log fold change value. This stat here is just a test statistic. You guys don't really need to worry about that for now, but there's basically just a test statistic that they used to come up with to like generate these p-values and adjusted p-values. Yeah, so and then we have a p-value here, and then we have p adjusted which is basically adjusted to be like a false discovery rate. And if we want to, we can also sort this to see the most significant ones based on this adjusted p-value. So if we print it out like this, that'll show us the most significant ones at the top. So yeah, this one was like very highly significant based on this adjusted p-value. Yeah, so that's what this result table shows us. So what we might want to do from here is we might want to get the ones that were significantly upregulated and significantly downregulated. So we could do that by defining a significance threshold. So I'm going to say significance threshold rho equals 0.01. This is a pretty low one, especially because I'm going to be using this for the adjusted p-value, not the raw p-value. So this is a pretty low threshold. But I'm using this because this project on this data set happens to give really a lot of differentially expressed genes. So this will at least help us narrow the list down at least a little bit. So yeah, I'll set that as the threshold. And then I'm going to say significant results, arrow equals results. And then we want all the rows, I'm going to say which results p adjusted less than significance threshold. So this is going to give us like a boolean to get all of these rows where the adjusted p-value is less than our threshold, and then we want all of the columns. So just comma here and then nothing because we want to get all the columns. Okay, so now we can check the dimensions of this significant results. And yeah, so now we have 7,822 significant differentially expressed genes, and then this 6 here is just these 6 columns of information we have. Okay, so now how do we find which ones are upregulated and downregulated? So the way we're going to do that is by saying significant results $log2 fold change. Basically, the ones where the log2 fold change is greater than 0, those are the upregulated ones. So if we just print this will just give us, again, like this table with all of the upregulated genes. But what we really want, or at least what I really want here, is the names of these genes. So I'm going to say row names to get the actual names of the genes out of here. I'm going to say upregulated. Okay. And then for downregulated, it's just going to be same thing, except we want the ones that are less than 0 for the log2 fold change. Well, then, of course, got to change this downregulated. Okay, then we can see how many we got for each one. So we can see length upregulated, 4,190 upregulated genes, and then length downregulated, 3,632 downregulated genes. And yeah, so that's quite a lot. That was actually more than I was originally expecting to get. But yes, that's the result for this part of the video at least. Something else to take into account is that if you guys were doing this kind of analysis for like a real life project that you were eventually going to be like maybe publishing in a paper, you might want to do additional controls, like additional adjustments and controlling for different variables before you actually do this analysis in this code here. So if you remember back to when in like the second lesson when we actually looked at the paper for this data set, I think they said in the paper, even in the abstract, that they when they were doing their differential expression analysis, they adjusted the expression data for different information about the subjects, including like the subject like race, gender, age, whether they smoke or not, and stuff like that. Because the idea is really to try to like see what differential expression is due to the IPF disease. So if you were doing this for like a real project, you may want to control for other variables that could be affecting the difference between the subject groups. But yeah, this is just like a kind of informal tutorial video, so I didn't do that in this video. But yeah, if you're going to like publish a paper on this, you may want to do like additional controls like that. Oh, also one more thing. Like I said before, all of the code here is going to be up on my GitHub if you guys want to like download it for yourself and try running it yourself and follow along. All of this code is going to be up on my GitHub. I'll put the link to it in the description. The only thing that's not going to be up there is the actual data set itself, because I don't know what the rules are about like distributing other people's data sets. I don't know if I'm allowed to do that on my own GitHub. But yeah, so that's going to be the only thing that's not going to be up on GitHub. But if you guys want to download this data set, you can download it on this the geo link here. And actually, if you guys have been following this series, we did that in the second lesson. So hopefully you guys already have it downloaded. But if not, you can find it at this link here. Okay, thanks for watching, and I'll see you guys next time.